say that in a material medium, if there is a dipole, it is in a material medium. It has to be a material definitely. Unless there is a material, you cannot have two poles. You cannot have electrons, or you cannot have charge. Charged particles have mass. Therefore, it has to be a material medium. Now then we define the dipole as a separation of two charges by an infinitesimal distance. And after that we saw that for dipole there is a polarization vector P, which is equal to epsilon 0 chi into E, applied electric field. When you apply electric field to a material medium, or if you have dipole, if you apply electric field to the dipole, then the dipole or the poles in the region where field is applied will align along the field. Therefore, they will be polarized along the field. So there will be polarization vector. So P is equal to epsilon 0 chi E. We said that let us assume that this dipole is oriented along z-axis or the z-axis, symmetrically around the z-axis, and the separation between them is very small, between the two poles is very small. Beyond that, we said that it is not a static electric field, it is an electric field which is time harmonic in nature, or we are applying AC electric AC. So alternating current is there. Because of that, the dipole will oscillate. If the dipole oscillates, then we said that its P, or the polarization vector, will also be time harmonic in nature. Now, in between, we discussed about chi, or the susceptibility. We defined susceptibility. Then we saw that D, the electric field flux density, is equal to epsilon 0 into 1 plus chi into E. That we wrote as epsilon 0 into E plus epsilon 0 into chi into E. Since we defined epsilon 0 into chi into E as P, therefore we defined D as D is equal to epsilon 0 E plus P. Now, from that we derived two new quantities based on the polarization of the material, not the field, not the field but the material. Based on polarization of the material, we derived two new entities. One we called as the polarization current density J pole. Other we called as polarization charge density rho pole. Now these two, as we know in the Maxwell's equation, if you introduce polarization current density and polarization charge density, they are responsible for generation of fields. And so from that, using that concept, we came back to find out the fields. For finding out the fields, we require the potentials. So vector potential A and scalar potential phi. Finding out the vector potential, as we already knew, it is mu or mu0 integration J. In this case, J is J polarized. So J polarized, then Z x minus x0 or r minus r0 into dV or dqr. That is, we took the convolution, or we convolved the Green's function G and the current. So that gives us the vector of potential. Similarly, we got the scalar potential phi by convolving the charge and the Green's function. So those are the things that we did. And then from the vector potential, we found out what is the H field. H is equal to 1 by mu A Corley. So using that, we found out what is H field. Then we found out E. E is equal to gradient of divergence of A minus del square A. So using that relation, we found out E expressions for explicit expressions for H and E we found out. Then in these expressions, we saw that there is a term which is falling off as 1 by R, and there are terms which are falling off as more than 1 by R or faster than 1 by R, which is either 1 by R square or 1 by R cube and 1 by R square. The terms that are falling off as 1 by R, we call that those terms are responsible for radiation, or those are the terms which we associated with radiation. Those terms are available in the far field or radiation field. Other terms are available in the near field. That we also proved that the terms falling off as 1 by R gives you radiation. How did you prove that? We proved it by finding the Poynting vector S is equal to half E cross H star, so that we considered only the 1 by R term. If you consider the terms which are falling off as 1 by R, then this S is a real vector. Integration of S over the area enclosing the charge or enclosing the current or enclosing the dipole, that gives you the total power. That also is a real vector. So total power is real if it is falling off as 1 by R. Therefore, when it falls off as 1 by R, it is radiating. So you got real power. When it falls off as more than 1 by R square, so it is 1 by R square or 1 by R cube, when it is falling like that, then S is imaginary in nature. Since S is imaginary, the total power is imaginary. Imaginary power means it is a stored power or a reactive power. So since it is a stored power or reactive power, that we call the near field. Then we saw the boundary between the near field and far field. That happens when Kr is equal to 1. When Kr is equal to 1, the magnitude of near field is equal to the magnitude of the far field. Beyond that, magnitude of the far field exceeds the magnitude of near field.
Sir, किसी पेज देखा जाऊँगी sir, show करूँगी.
पेज में चेंज कर फास्ट पेज रहेगा.
आगे.
हम गला क्लास में जहाँ डिस्कशन करते ले, उनका को समराइज करते. So then we saw this. And that the near field, so the range Kr is equal to 1 is the boundary between the near field and far field. So if you know what is the range, then if you draw a radius R, which is equal to 1 by K or lambda by 2 pi, so if you draw a sphere with this radius, the region within this sphere is near field. Region outside this sphere is called the far field region, and that region, the region which is within the sphere, is called the radian sphere. The sphere is called the radian sphere. Within the radian sphere, we have the near field, both non-radiating near field and the radiating near field, both will be within this sphere. So this is what we saw. Then with that, we will come to today's lecture, which is far field approximation. In this far field approximation, what we will do is we will consider only the far field portion of the fields. So we have got electric field and magnetic field, and we will consider only their far fields. We neglect their near field. Now, how do you find field? That we have seen from the vector potential, we find the fields. So can we find a vector potential which gives us only the far field? Near field, it does not give us the near field. That is what we are going to investigate. So today's lecture will be, the outline of today's lecture is, first we will do a look at the assumptions that we will make, then we will go to the approximations that we are making, Then we'll go to justifications regarding these approximations. Then we'll go to the conditions for far field. Then we'll go to characterization of the far field. Then we'll come to what is radiation field, and then we'll come to radiation vector. Then we'll come to radiation potential, and then after radiation potential we'll discuss little bit about the coordinate system or refresh our ideas on coordinate systems. Then we'll come on to what is called spherical length, linear length. You know what is spherical length, that we'll discuss. Then we'll come on the radiation field computation, how to compute the radiation field, that we'll see. Then we'll see what is radiation vector and decompose the radiation vector. Finally, we'll see the radiation field components. So this is what we are going to do in today's discussion. So let us start with the assumptions. Okay, next. So for assumption, remember, if we are considering a radiation problem, we have a source. The source is radiating electromagnetic wave. So we have a sink, or we have a source point, we have an observation point. Here the source point will be designated by prime. So the source point here is P dash, that is the source point. Its vector, position vector is R dash. O is the origin, or O is the center of the coordinate system. So O is the origin. So O to P dash, if you join a vector, that is R dash. Similarly, the observation point is P. Its radius, its position vector is R. So join O to P, that vector is R vector. Then if I join P dash to P, that will also give me a vector. Now we have got a triangle OP dash P. OP dash is a vector, OP is a vector, P dash P is a vector. Now OP dash vector plus P dash P vector is equal to OP vector. That you know from vector addition, basic vector addition, that gives us. So OP dash plus P dash P is equal to OP, or P dash P is equal to OP minus OP dash. OP is the vector R, OP dash is the vector R dash. Therefore, if the vector P dash P is capital R, then capital R, or the magnitude of capital R, is equal to R minus R dash magnitude. Now R minus R dash magnitude, let us find out what will be R minus R dash magnitude. That will be approximately R minus R cap dot R dash. What is R cap? R cap is the unit vector of the vector R. How do you establish that? To establish that, what we do is we drop a perpendicular from P dash onto OP. So that perpendicular meets OP at Q. Angle between this OP dash and OP is alpha. Then we can find out R dash into R cap. R cap is along R. Therefore, R dash dot R cap, or R cap dot R is equal R dash is equal to R dash cos alpha. Why it is R dash cos alpha? Because R cap magnitude is 1. So 1 into R dash into cos alpha, that gives you R dash cos alpha. R dash cos alpha will be OQ. That is the size OQ. So now you can find out what is R minus R dash. R minus R dash is, you can see, if I have dropped this perpendicular from P dash onto OP, that meets at Q, and P is at a large distance, then P dash P is approximately equal to Q dash Q. Therefore, R minus R dash is approximately equal to OP minus QR, because OP minus QP, because QP will be approximately equal to P dash P, which is if P is at a very large distance. So if that is done, then OQ is equal to R cap dot R dash. Using that, we get capital R is equal to R minus R cap dot R dash. So with this geometrical background, let us assume that the field point R is very far from the current source that we have discussed now, and then that means it is very far from the current source, means R is much greater than R dash, which is typically spatial extent of the current distribution. What is typical current spatial extent? That is R dash. R dash is the typical spatial extent. Spatial extent means extended in space. What is the expansion in space? That is the spatial extent. So R varies only over the current source, and the capital R, which is much greater than L being typical extent of the current distribution. Now I am not going to discuss about this. We have already discussed this. So let us come to the next approximation. Under this, what are the approximations that we are going to make? So the first approximation is, let us expand R. Let us expand R in terms of R dash by R using Taylor series up to the second order. So second order, up to the second order term or second term will make the expansion of R. Now what is R? R is equal to absolute difference between R minus R dash. Now R minus R dash, that you can say is root over of R square minus 2R R dash cos alpha plus R dash square. Why this happens? R square minus 2R R dash cos alpha plus R dash square, and that you know Q dash, or this R minus R dash, if you find out the absolute of a vector, then it is the square root of the square of the vector. So square of the vector is R minus R dash, its square is R square plus R dash square minus 2R dot R dash. R dot R dash is 2R R dash cos alpha. So that we are taking the square root of that. Now from that, let us take R common, because R is much larger than R dash. So we will take R common. If we take R common, then it is R into square root of 1 minus 2 R dash by R cos alpha plus R dash by R square. Now let us expand that the square root term using binomial or Taylor series expansion. Let us expand the square root term. So that will be approximately R into, within the square root whatever is that, if you expand, that will be 1 minus R dash by R cos alpha. Why? Because that will be 1 minus 1 by 2 into 2 R dash by R cos alpha, the second term. So that will be 1 by 2 will be multiplied in the second term. That gives you R dash by R cos alpha. Then multiply 1 by 2 in the third term. 1 by 2 when you multiply in the third term, that gives you 1 by 2 R dash by R square. So that you can write as 2 times R dash by 2R square. So this is the first order. Then the second order is you divide it by 1 by 8. So that we will do minus 1 by 8 into minus 2 R dash by R cos alpha, then plus R dash by R square whole square. So now if I expand that and simplify, that will be approximately equal to R into 1 will remain as it is. Second term R dash by R cos alpha, that remains as it is. Third term is plus 2 R dash by 2R square, that remains as it is. Then the fourth term is 2 R dash by 2R whole square, that is the whole square into cos square alpha, that remains as it is. The last term is higher order term, so that will be dropped. Now when R is much greater than R dash, under that condition you can see r dash by r, that will become r dash by r into r dash by r will become r, okay, no. So now capital R will be equal to multiply r in all the terms. So if I multiply r in all the terms, the first term is r into 1, so that is 1 r. Second term is r dash by r cos alpha into r, so that is r dash cos alpha, plus third term is 2 r dash by 2r square. So if you take that common, r2 r dash by 2r square common, then within bracket will be 1 minus cos square alpha, which is sin square alpha. So 2 r dash by 2r square into sin square alpha. This is valid for r much greater than r dash. This we have done the approximation that r is much greater than r dash. Then only the expansion, the first approximation we took in the third line, that is valid. Therefore, this is what is capital R. Now, for when you use this R in the numerator, when you use this R in the numerators, then capital R, when we use this capital R in the numerator, then capital R will be equal to R minus R dash cos alpha, or that you can write as R minus R cap dot R dash. If you are using it in the denominator, why it is, what happens to the third term? Third term is dropped down because we are considering it up to the second order term. Third term is third order term, higher order term, second square. So since square comes in, so third term is dropped out because we are considering up to second order term. So third term is dropped. When we use it in the denominator, the capital R is used in denominator, then we write capital R is equal to R minus R dash cos alpha, or R capital R is equal to R minus R cap dot R dash. That will be taken as approximately equal to R, since capital small r is much greater than small r dash. So that is, in the denominator we take capital R approximately equal to R, because R dash is very small compared to R, and R dash can be dropped compared to R. So that is why in the denominator we take it as small r. But in the numerator we do not do that. The region will be clear later as we proceed in our discussion. Region will be clear later. So R is equal to R minus R dash cos alpha in the numerator, or R is equal to R minus R cap dot R dash. That is what we are going to use. Now let us justify this numerator and denominator. Next. Now there are inconsistencies in the approximation in the exponent and denominator. In the numerator and denominator we have inconsistent approximations for capital R. Why? Reason is R cap dot R dash, they cannot be neglected for multiple expansion. The R cap dot R dash that exists in the numerator, that cannot be neglected for multiple expansion. If you are doing a multiple number of poles are there and you are expanding that, we cannot neglect R cap dot R dash. And usually multiple expansion occurs in the numerator. Therefore, you cannot neglect it. This can be neglected in the denominator for radiation problem because it does not affect field distribution in space of propagating wave. As you propagate at a large distance, so if you are moving at thousands, suppose you are considering 500 kilometers. So from the source you are at 500 kilometers, and the source is at a distance of 2 meters or 10 meters from the origin. From the origin, the observation point is 500 kilometers and the source is 2 meters. Then the difference between the observation point and source, which is 500 kilometers minus 2 meters, that will be approximately equal to 500 kilometers. It will be very small. So in terms of kilometer, it will be very small. Therefore, it will be 500 kilometer approximately. So therefore we can neglect it in the denominator. Next. Now we are neglecting the second and higher order terms in the exponent. Exponent means in the numerator e to the power. Exponent is exponential. I hope you remember the potential A contains the term Green's function. From Green's function formula is exponential minus jkr by 4 pi r. So that in the numerator we have exponential minus jkr. So that is why exponent we are saying. So if you neglect the second and higher order terms in the exponent in the numerator, then they can be multiplied by k. These exponents must be approximately equal to 1 when they are multiplied by k in the numerator. When we are neglecting them, the second and higher order terms, they must be multiplied. They are to be multiplied by k, multiply them by k. Then these exponent terms, because k r e to the power j k r, so k r is multiplied by k. So these exponent terms, this k r must be equal to approximately equal to 1 in the far field. So in addition to r much greater than r dash, we must have k r dash by r less than much less than 1, which means r is much greater than 2 pi r dash square by lambda. This is what we have seen already earlier. So r has to be much greater than 2 pi r dash square by lambda to be in the far field. So when we have 2 r dash is equal to d, d being the diameter of a sphere which is enclosing the antenna, when that happens under the negligence of second higher order term, then we get r is much greater than pi d square by 2 lambda. So that you can see for r much greater than 2 pi r dash square by lambda. Now 2 pi r dash square, that you can write as 4 pi into 4 pi r dash square by 2 lambda. So 4 r dash square is 2 r dash square, 2 r dash whole square. 2 r dash is equal to d. Therefore in the numerator now you get pi d square divided by 2 lambda. So r has to be much greater than pi d square by 2 lambda. So this is the range where you will get the far field. So if r is much greater than pi d square by 2 lambda, we get the far field. So now we will come to the far field conditions under which we get the far field. By convention, let us approximate pi approximately equal to 4, because pi is greater than 3, less than 4, so we will take the higher side, pi approximately 4. Now we have got r much greater than 2d square by lambda. With this approximation pi approximately equal to 4, we get this 2d lambda. Then we will come to the far field condition. Then we will get the far field condition. Far field condition is, first condition is r has to be much greater than r dash. The distance of the observation point must be much greater than the distance of the from this to the source point. Then the second condition is distance to the observation point should be much greater than 2d square by lambda. So these are the two conditions. Now from this second condition, we can see that when d is of the order of lambda or d is greater than lambda, either of these two, when d is of the order of lambda or d is greater than lambda, then b is essentially equal to a. So b and a are equivalent if d is of the order of lambda or d is greater than lambda. But when d is much smaller than lambda, then a implies b. So from b you will get a only when d is of the order of lambda or d is greater than lambda. When d is much smaller than lambda, then a automatically implies b. So these are the far field conditions. So if you have a sphere of diameter d enclosing the antenna, to reach the far field you should have R, the source, where you are, sorry, source, the observation distance from the origin or antenna should be 2d square by lambda, with d of the order of lambda or greater than lambda. Otherwise, if d is much less than lambda, then R has to be greater than R dash. Now let us try to characterize the far field. When we are in the far field, what will happen? I will find out the dividing line between the far field, which is called the Fraunhofer zone in diffraction, and the near field, which is called the Fresnel region. So two regions are there, far field region and near field region, or Fraunhofer region and Fresnel region. Fraunhofer and Fresnel you might have read when you have read optics. Now on this dividing line is R. When R is equal to 2d square by lambda, so that line is called the dividing line. So R is equal to 2d square by lambda. Within that we get the radiation sphere type of thing. So within that, d is the sphere which is enclosing the source. 2d square by lambda is the sphere around the source, the radius of the sphere which is around the source, and within this radius the field is called the Fresnel field or the near field region. Outside this source, 2d square by lambda, that is called the far field or the Fraunhofer region. Now, what are the properties of the far field? The properties are the radiation angular distribution, which means the distribution in theta and phi, they are independent upon R. So irrespective of at what distance you are, once you cross this limit 2d square by lambda, if you vary theta and phi, the radiation pattern or the way the field is distributed over the angle theta and phi is independent upon the distance from the source if you are in the far field. So that is one characteristics or the main characteristics of the far field. Then there is a possibility of ignoring the first order term r cap dot r dash from the exponent. That possibility comes under the condition k r dash is less than 1, much less than 1, or r dash is much less than lambda. So this is the condition. This shows that this is possible if k r dash is much less than 1 or r dash is much less than lambda. R dash is the distance to the source, and that is much less than lambda. Lambda is the wavelength. So distance to the source is much less than the wavelength, which means the size of the source is very small compared to wavelength. Therefore, this type of antenna are called electrically short antenna. So this is possible only for electrically short antenna. If you have an electrically short antenna, then d is much less than lambda, or the sphere enclosing the antenna is much smaller compared to the wavelength. Then this occurs for long wavelength or low frequency limit in the low frequency limit, or for long wavelength this occurs. Example is the Hertzian dipole. With this we will take a break. Now, once we have characterized far fields, we will take a break. We will come back and study about radiation vector in 5 minutes.